Now we're going to turn our attention towards stating an important fact that we're going to actually use very, very heavily throughout many of the next sections. In fact, this idea will be asked and used when it comes to exam number 5. On that exam, I'm going to definitely be dealing with a question where you're going to have to work with a couple different surfaces, kind of all in unison. And here's kind of how we work with this. We'll see that this property is kind of an extension of a property of line integrals. So let's suppose that sigma is a finite union of smooth surfaces. So like a bunch of different surfaces all compiled together to make sigma. And so maybe we break apart those individual pieces of sigma by calling them sigma 1, sigma 2, all the way up to sigma n. Well, then we could say that sigma is piecewise smooth. Each of the pieces is smooth. Well, then if I wanted to do a surface integral over all of sigma, you can notice how easy that would be. I just kind of have to do a surface integral along each of its pieces, and then just add everything up together. So as an example of this, let's take a look down here at example number 4. Suppose that sigma is a can without a top, which consists of sigma 1. We'll see here that this kind of represents a circle that's being stretched vertically. So let's see if I can actually go ahead here and try to create a picture of something like this. Okay, so maybe I have something that looks like this, and I have something that looks like this, and then I'm going to go ahead and put some lines in on the side. Oops, that seems to be a little bit long. Let's try that again. Okay, so something kind of like that. Okay. Ooh, I might actually be able to do, I don't think into shape actually is going to work. Okay, but you can imagine what I have here, right? That this right here is going to represent a nice cylinder. Okay? And so what we have is a cylinder shape like this, but it's without a top. So we can kind of imagine that maybe everything over here is shaded in. Even the bottom of the can is shaded in, but there's nothing on the top. And so if sigma 1 forms the wall, then sigma 2 is forming this bottom. It's the circle with everything filled in at height z is equal to 0. So we could actually even imagine further still that this is kind of maybe resting exactly on top of our x, y, z axes, kind of in the following way. Okay, well again, if I wanted to find the surface integral, or a surface integral, over this particular surface of sigma, which remember is all of this combined, I might need to try to go ahead and find a surface integral for each of the individual pieces. So let's suppose I take a look at the first piece, sigma 1. Now I'm giving away right here at the beginning that I'm going to take the parameterization approach. But let's think about why, because you might recall in the last video we said that sometimes we can avoid doing the parameterization as long as we have a nice z equals formula that describes our surface. Well, in this case I can probably see that sigma 1 is not given to me in a z equals format, but more than that, I can see that if sigma 1 is this wall of the cylinder, it is certainly not going to be a function, right? There are many values of xy, or there's a value of xy that produces a whole bunch of different z coordinates. This would not pass like a vertical line test for surfaces. So since I don't have this z equals format, I'm going to be forced to try to go ahead and approach this using a parameterization. So let's suppose I want to find a parameterization here. If I look again, I can see that based on how sigma 1's defined, there's a relationship between x's and y's, and there also happens to be unrelated value of z. But I think that determining this then should actually be pretty simple. Now, I'm going to go ahead and note that since z kind of operates all on its own, why don't we just give it the variable of v? Right? It's totally independent off by itself, and we can even state where v is going to range from. Clearly v goes from 0 to 2. But u is going to have to be used to describe the circular relationship that exists between x and y. And now it's really tempting to go ahead and say, let's let x be equal to a value of u, and then try to figure out some giant mess of stuff to put in there for y. But actually, that's going to be really complicated to do, because it's going to require that, like, I get a square root and a whole bunch of other things going, and like, I don't want to have to deal with that. that's not ideal. So instead, I'm going to go ahead here and I'm going to say that how about we go ahead and, oops, let me delete that as well. How about we go ahead and define this circular relationship using trig functions? Again, I know that if I was to do something like a cosine of u and a sine, oops, sorry about that. Well, that's why I have my ink to shape on. Okay, that's why it's being weird. But if I have my cosine of u and my sine of u, that's going to allow for a circular relationship between these variables. And if I want to go around a full circle, then u should be defined from 0 to 2 pi. It should also be the case that the number in front of the sine and cosine represents the radius of the circle, and so since my radius here is 1, I'm going to leave this as 1. So this seems like a perfect representation for what I have here. This is great. Now, I can go ahead and if I take a look at the next page, I can see that it's actually possible then to try to find a parameterization. I'll call it by a different name. Let's call it S for sigma number 2. Well, remember, sigma number 2 is the bottom of the can. And now, I may not need to find a parameterization, but if I'm not going to do that, I'd have to find a formula, z equals, that tells me exactly this bottom surface. And while that might be possible to do, you could imagine maybe selecting z is equal to 0, defining the range of x's and y's on that region then becomes a little bit more difficult. So I'm going to go ahead and just stick to the parameterization route. So I'm going to find a z of uv. Now again, this should be pretty easy because I have a circular relationship here, and I want to go ahead and also think about how I would define that circular relationship, and also how I can make sure that I'm also filling in the entirety of that circle. So it's important that I not only have the circle exterior, but also everything on the inside. Now this creates something kind of interesting and a bit more complex. Let's suppose that I start with cosine of u and sine of u to help get the circular relationship in the xy direction. Again, it's pretty easy to see that the range on u would be 0 to 2 pi. And it's also probably easy to see what I want for the value of z. Because in this case, I don't actually need to put a v here, because notice that the z doesn't vary on that bottom portion of the cylinder. In fact, there, my z is always a 0. But then notice that there's no value of v that's really being made use of here, and I need a value of v. But here's the dilemma, and where this value of v comes in. Notice that if I was to graph this, this is only going to graph points that exist along the edge of this circle. It's not going to currently graph any points that would be on the interior of that circle. So here's what I'm going to use. I'm going to select v to act as like the radius of the different circles that I will draw. And I can think about the range of radii that I want in order to fill in this entire circle. So imagine this as a circle with a whole bunch of circles embedded inside of it, kind of all wrapped around each other. Like I have a circle like this, and then a circle around it, and a circle around it, and a circle around it, and a circle around it. And what do the radii of those different circles have to range between? Well, the smallest here would be 0, and the largest should be 1. So I go all the way out to that biggest radius. So this is a way I can kind of create a disk that gets filled in using a parameterization. Well, once I have this, notice that it's really easy now to evaluate part C and this surface integral that's given here. So based on the fact that we established at the beginning of this video, we know that if I wanted to go ahead and compute this, all I would have to do is to say that I can just break this up into first doing the surface integral over sigma 1, and then doing the surface integral over sigma 2. And as long as I can compute each of these, everything's going to be good to go. Now, of course, that means that each of these is going to have to be converted one at a time. So I'll have to use the S parameterization to work over here and to replace my x, my y, and my z. I'll also have to do a cross product calculation for the partials of S with respect to u and v to help replace the ds. And I'll have to do similar sorts of computations for my sigma 1 and my r parameterization. Now in this video, I'm not going to do that, but I'm going to leave it to you to try to go ahead and compute each of these and see if you can work down to a final answer. There's definitely a little bit of work to be done here, but it'll be good for you to try to practice it on your own and compare to the solutions that are up online. I will tell you though that the final answer that I got to was 59 pi over 6. Okay, if you have any questions about this section, please, of course, make sure that you let me know. But I'm definitely going to reiterate again in this video how important it is to understand two things from this section. One is that I had two different approaches to tackle surface integrals. One was by creating parameterizations, but the other from the last video was by dealing with things that were given in function form, and I have to understand that difference. The second thing is what I said would definitely be asked of you on exam number 5, which is it's important that I understand that if I'm given a surface that has multiple components to it, that I can go ahead and imagine breaking that surface up into each component and tackling them separately and taking their sum to find the entire surface integral.